Okay, so as per usual, we'll start with the Kahoot. I'm not sure who is running the Kahoot today. Warren, you're running it? Okay, great. So I'm going to close one of our doors. The meeting is quite annoying.
Do you need other doors also?
Yeah, we can try to do that.
Okay.
Whether if anyone is coming in, we'll just try to open it up. Okay, so as usual, we're going to ask all of you to scan in. Okay, so we have 1, 2, 3, 4, 5 of us in the audience. I think there were a couple people who are not able to join us physically because, well, today is NUS Well-Being Day, right? So we're actually not supposed to be here, but it's actually too much work to try to reschedule. I didn't get my act together. So apologies for that. The other thing is, of course, that it's sort of ironic. We're talking about harms on a well-being day, but you know, somehow coincidentally that works out. Okay, so we'll just wait for a couple more minutes for everyone to come in. So if you haven't already, join Kahoot by typing in the game pin into kahoot.it. Okay, and the information is there. I just want to share with you a couple other announcements. Okay, I should close this. This has the answers. So if you haven't already, which is that STEPS is coming. As we know, it's on the 15th of November. So let me just close this sidebar. Okay, so it's Wednesday next week. And then the event actually starts at 3 p.m. Okay, so actually I thought it started later than that, but actually the event happens from 3 to 7 p.m. So do come during that period, even for our external guests that are participating. I hope you will be able to take some time off to come down the steps to showcase your work. And if you are able to make it, you already have, I think, your buffet dinner coupon so that you can get some food, all right? So between 3 o'clock to 5 o'clock, it says here there is voting, okay? So voting is a regular thing in steps, all right? So people will be asked, you'll be asked actually to go to another courses, projects and vote on the best ones, okay? So if you go to Events now, and I think Victor also said there's some problem with Events login, right? Yeah, it takes a long time to load, but it's here somewhere. Let's see. Yeah, here it is.
You should go to tracks and there's one.
Yeah, you can see the various tracks here. So there's a couple different tracks. There's digital markets, which is the LLM course for applications. So they're doing applications of LLMs. There's the game development project, always the mainstay because the main organizer is the game development group. There's the information systems capstone. There are people from their FYP projects, and there's us, 6101. Okay. So you can see ours looks the least interesting, right? Because you guys haven't been able to log in and fill the things in. But I hope you guys will actually put your information there, okay? So I'll be haranguing you and reminding you over the next weekend or so, you know, even though it's Well-Being Day and Deepavali, you know, to try to put in some things. I mean, it would be nice if we were as put together as these groups because they all have much more information, especially I think every time it's our games development group has the most, right? They have a lot of projects and they have videos and things like that. But the whole point is like, if you do a good job here, I think projects, okay, and being able to do that. If your project is missing from this listing because you came in late for 6101, I think Yu Hong and one other student in his group haven't been put up here. Don't worry, I will go fix that soon. Okay, yeah, go ahead.
My group too.
Your group as well. Okay, so on the project channel, you can just write a short even now, Min, you haven't put me in the project. I need to put it there, okay? Then you'll be able to log in, put your things up and take it from there. So just again, the reminder, it is Wednesday the 15th next week. Okay, whatever you present there, it is not counted as archival information. So it doesn't bar you from double-blind submission of conferences. Okay, so anything like that is fine. Okay, and then there will be opportunities to network with people, especially for undergraduates or other people. You may want to look for people who would like to take you as an intern, for example. Okay, and then there'll be a closing ceremony. I hope all of us will be able to stay for the closing, because usually we try to take a group picture, okay, there. So all of us can come and take the group picture. And then again, Friday night, which is not Wednesday, after steps Friday is our last class on privacy. And after that, we will go to a local restaurant or bar to hang out, okay, if you'd like to, okay. It is week 13. I know some of you are really worried about projects and finals, so you're not compelled to join. I mean, it's a social event. But I think especially a lot of our graduate students feel like there's not a lot of time to network, right? So I hope you guys will join me and come with us to someplace to just talk shop, okay? So especially those of you who are not here today, who are listening, who are external guests for the course, I hope you can join for that. Okay, all right. So I think we can start with Kahoot. Let me just close this. Yeah, and the other thing I'll tell you about the projects is that we are in SR1. We're actually the only course that's supposed to be in SR1. So everything else is outside, okay? But we got the whole SR1 seminar room to ourselves. If you look at the seating chart, there's somebody at the door. We're actually over here. So there are half of the group projects on one side and the other half on the other side. Okay. So if you've been to SR1, you know it's a big area. Okay, you can sit on either side and use the space up for that. Okay. So yeah, I think we'll go ahead and start. If you haven't already, we'll give you a couple, maybe a minute or less to scan the QR code for the Kahoot. Let's see, where did it go? Okay. Okay, everyone scanned already? Anyone in here who hasn't scanned yet? Just raise your hand so we can wait for you. Okay, yeah, Victor, go ahead. Okay, and Warren is kind of done the Kahoot, so you can take it away when you're ready.
Right.
Okay.
Do we need at least 10 people? It's like
Anyone else?
no one else not inside yet.
All good? Okay, yeah, let's
Okay.
start. Thank you. If the music is too loud, just let us know. We can turn it down. Because that was a problem last time.
So the first question is what's the full name of clip? It's a very simple one, I guess.
I like
so-
your paperclip.
Yeah, it's Clippy from the Microsoft.
Yeah, notoriously bad.
Yeah. So it's contrastive learning, language image pre-training, because we're actually doing contrastive learning on all of the inputs. So you're trying to like distance away those that are not similar to each other. And the images and text that are similar to each other, we're trying to cluster them together. So that's why you're doing contrastive learning, and that's why it's called contrastive language image pre-training instead of the rest. So yeah, next on the top of the board, and then there's Taha and Yo-Yo as well at second and third place. So I'll go to the next question. So which statements are true about clip? So the answer is actually the first two, because firstly, Clip was trained to actually find the cosine similarity of images in text embeddings, because it's, again, like similar to the previous question, it's about contrastive learning. So you're trying to find those that are images in text that are similar to each other. And then also, Clip is very strong in zero-shot transferability, because it's trained on like a very large data set before it was actually before any fine-tuning. So it actually has very good pre-training already. So if you just use Clip directly on like maybe a bicycle, it's able to capture out and say that's a bicycle. For the next 2 points, right, it's not really true, because it actually scales very well, because the pre-training was done on like, I think, web scale noisy text. So that really like contradicts both of the last 2 points, because firstly, it can actually scale to like a very large data set, and it's also able to be used in a lot of different applications. That's why a lot of different models still use Clip until now. Then for Clip cannot work on noisy data, the original pre-training that Clip was used, that Clip was trained on, was actually like I think web scale noisy text supervision. So actually it can work on noisy data. So that's why the last two are wrong. So yeah, now 7 Elk Musk is at the top, and Taha is still second and third. Yeah, OpenAI Dev Day just like dropped, I think, a few days ago. So I think there's a reference to that as well. So the next question is, how does the Q formula to actually align text to images?
Your yellow option.
Yeah. Yeah, so the answer is actually, it can actually share the self-attention across both its images and text transformers, because how Q transformer works, according to, I think, Yan Leong, who presented at last week, is that you have both an image transformer and a text transformer, but then the self-attention is actually shared with each other. That's why you can actually take both. You can actually like query for like both of the image and text token together. So that's how it actually aligns all of the tokens. But then for the red color one, where it concatenates like image embeddings directly to text embeddings, we don't really do that, because we talked about it last week, where we talked about this thing called like tokenization and subwords, and similar concept for multimodal. If let's say you have a LLM trained on like a certain subword, and you use like an input from another subword, then what will happen is that it might not really understand the different subwords that is used. It's the same thing for multimodal tokens. If let's say LLM was trained on like just like text, and suddenly you just give it image embeddings, it might not actually understand or use the image embeddings that well. So that's why red is wrong. For yellow, it's not actually questionable. It's actually querying transformer. So that's also wrong. And then for the green one, that's actually from the animal paper, not from BIP2. So that's why only blue is correct. So yeah, 7 Outman is still at the top. And then there's still Yo and Ta. So let's go to the next question. So the next question is a very simple one. What's the 3 rows split by the LM in GPT-4 So that's correct. Like based on the slides, right, it was actually red, green, and blue, because these are the 3 rows they actually mentioned in the paper and in the slides as well. But for toolmaker, we don't actually consider that, because the authors didn't talk about any toolmakers at all. And the next part is actually, the toolmaker is a reference to another paper by I think another author. So it's like LM has toolmakers, and that's similar to GPT-4 tools, but it's about actually having like a large language model create coding tools instead. So that's a very interesting project that you guys can actually read up if you are interested. And so Salmon Almond is still on top, and Taha and Yo is at second and third place. So now we go on to asking about Palm E and what kind of like modalities does it use. So actually everything is correct, because based on the slides, like all 4 inside, but I think just to make sense of like all the answers, because Palm E actually uses both vision and like text to try and like create like an embodied robot that can actually like visualize its environment. So I think that's why like the first 3, the red, blue, and yellow, right, you need all those 3, because you want to detect what objects are in the area, as well as also to like kind of identify visual concepts. But then for like the green color one, it's more like a scene representation. I don't exactly know why they used it, but the authors just added that in as a modality. So yeah, to the next question. And Sam Altman is still on top, followed by Yo and Ta. It's very interesting. So this is a true-false question, and it's asking whether can it take in multiple modalities in a single conversation, which means like given like a prompt, right, can I input like text, images, and everything as well? Oh, yeah, so actually it's true because in the prompt above, you can see it taking multiple modalities. So you can actually take in multiple modalities, you can give it audio, vision, as well as text all in one go, and it will still be able to like understand everything and try and merge everything into one single conversation. So if you look at like the preview, the show media, yeah, it's a bit small, so let me see if I can zoom in. Yeah, I can't really zoom in here, but basically you can see it's taking in multiple modalities, and then from there, it's able to give a very like relevant output. So yes, it can actually take in multiple modalities. So SAM1 is still at the top, followed by Keyou and Taha, which is and they're actually, I think, closing up by a bit. So how does NextGPT actually decide which modality to use? And yeah, the image I found like the com lab, so I just took it and pasted it here. So the answer is actually blue, not yellow, because we don't actually use mixture of experts. It's a very similar concept to mixture of experts, but they just get the LM to actually just generate the signal token to actually and then append it to like the output so that it knows where to actually go. Whereas for mixture of experts, I think the presenter also talked about mixture of experts. The difference is that there's a gating function, but we don't have that in this current like implementation. For the red color one, they are not appended by a different classifier because it's actually the LM doing all the appending and also appending like predicting which like signal should go to like the output. We don't use an external classifier for that. And lastly, the green one is wrong because the authors can't really use RNG for like a research paper. Oh, so you actually beat Sam Altman because I think Sam Altman thought it was RNG. But let's continue. Maybe that's why I give everyone 500 OpenAI credits.
Okay, last
Yeah,
one.
the last one is about the key components of Motion GPT. So the answer is actually all three, except for the green color one, because I'm not sure whether the paper did discuss about this, but based on the slides alone, I don't think there was any mention of any motion image position embeddings, because usually position embedding is just for like text. We don't really use it for like the image embeddings, I believe. But the red, blue, and yellow was actually all mentioned inside the paper, and then they also talk about these three being like very important parts. So yeah, that's all for like this question. So here's the podium. So in third place we have Taha. In second place, we have Sam Altman. And then in the first place, we have a bit of a glitch, but it's Keyou. Yeah. So yeah, that's it. Then but this is just AI system.
Yeah, that's just AI. Okay, let's thank Warren for a nice narration of the Kahoot today.
So you will have noticed there is a week 13 Kahoot, but there's no time to play it. So that means week 13, we're actually going to do the Kahoot at the very end of lecture. Ah, okay. So that means that will be actually the last activity we do in this course. Okay. All right, so we're going to go to our slides. Just a reminder where the scribe document is. It's the same place. You can take the URL that's listed down here and then add -scribe to it, and then you get there. So we'll go ahead and have our presentation. So I think Minzhi and Xinyuan are presenting. Are you guys ready to present?
Yes.
Okay. So I'm going to give you remote control. I think I can do that. Let's see. I don't know. Who is doing the navigation? Is it Xinyuan or Minzhi?
I will present the first paper and Xinyuan will present the second paper.
Okay, so I've given you slide controls. Can you see it?
Mm.
Okay, if not, what we'll do is we'll stop screen sharing and then you can share your screen, okay?
Okay.
Okay, then you can take over the screen.
Can you see the screen share?
Yes.
Oh, nice. Then I will just start now. Hello everyone. Today we are going to talk about harms in language models generally, and Xinyuan and I will give you an overview with two papers. So the first paper is socio-technical harms of algorithmic systems, which proposes a taxonomy for different harm types. And the second paper Xinyuan will be presenting is language generation models can cause harm, talking about different intervention strategies to reduce harm. Okay. So let's dive deeper into the first paper about socio-technical harms. So the literature underscores harm as a relational outcome of entangled dynamics between design decisions, norms, and power. The concept of socio-technical harms acknowledges the interplay of two key factors, which are technical system and social factors. Motivation of this work is that a larger number of literature has identified a wide range of harms across different technologies. However, practitioners lack a high-level and synthesized overview of harms from algorithm systems. Based on a scoping review of 172 papers, the authors present an applied taxonomy of different socio-technical harms to support a more systematic surfacing of the potential harms in algorithmic systems. The final taxonomy they propose is built on existing taxonomies, classifications, and previous terminologies. The research contributes to the community by offering a scoping review of harms, creating organized snapshots of articulations of computational and contextual harms, a reflexive thematic analysis of harm definitions, as well as support for interdisciplinary communication by providing terms and definitions. Also, they provide some implication for future work. So here is the methodology they adopt to come out with the taxonomy in their paper. There are 4 steps, which are identify research questions, identify and select relevant studies, followed by data charting and collecting and summarizing results. I will talk about each step in this methodology. So for identify research question, they developed 3 research questions. The first one is asking about what harms are described in previous research on algorithm systems. How are the harms framed in terms of the impacts across micro, meso, or macro levels of society? And the second research question is to study where is their conceptual alignments on different types of harms from algorithmic systems in the organizational structure. And the third research question is on how do gaps and absences research in socio-technical harms suggest future opportunities for research. And the second step is to identify and select relevant studies. In this step, the authors employ multiple strategies to identify relevant resources through different sources, such as electronic scholarly databases, a citation-based review, and targeted keyword searches in relevant organizations and conferences. So the keyword term they include algorithmic harm, socio-technical harm, AI harm, harm taxonomy, allocative harm, etc., to search for relevant literature. And after the searching, they did data charting. They employ a descriptive analytical method for charting data, which is a process of synthesizing and interpreting qualitative data by sifting, charting, and sorting material according to key issues and themes. 2 researchers independently charted the data through reading of the full text of each source and organized them into a spreadsheet, specifying characteristics of the source and description of the harm. discovery of a new concept or type of harm resulted in a new code of harm. And it is quite difficult to know when to stop for searching, so they define a term called theoretical saturation, which means a point at which coding additional papers or resource does not yield additional themes. Then the last step is collecting and summarizing the results they have. So they adopt this framework called Brown and Clark, which describes a step-by-step summarization process. Firstly, it starts with familiarization with the data, followed by coding the phase. And after that, they search for relevant themes for the data, and they review the theme and define and name the new themes and conclude the whole process with the summary. Okay, after talking about the methodology, I think here comes the interesting parts of the results they have, the main result they have, which is the comprehensive taxonomy. From this graph, we can see different types of harms in language models. There are 5 main types of harm, which are representational, allocative, quality of service, interpersonal, and social systems harms. And I will talk about each subcategory inside each main category with some illustration or examples. So for representational harm, it mainly deals about representation of different social groups. And within this category, the first type is stereotyping social groups. So it means how the system's outputs reflects beliefs about the characteristics, attributes, and behaviors of members of certain groups. They marginalized in society, the group marginalized in society face numerous stereotypes conveyed in various types of data and coding schema. And one example is that how gendered beliefs about women's submissiveness are reflected in digital assistants. And the second subcategory is demeaning social groups. The systems can lead to demeaning treatments of certain social groups. This harm subtype was also popularized by previous research, which describes it as an action which demeans certain social groups to when they are cast as being lower status or less deserving of respect. And the next type, the eraser of social groups, means that people, attributes, or artifacts associated with specific social groups are systematically absent or underrepresented in the whole system. And the next type, alienating social groups, means when an image, one example is when an image tagging system does not acknowledge the relevance of someone's membership in a specific social group to what is depicted in the images. And the next type, denying people the opportunity to self-identify, means that people cannot self-identify their social relation in this system. They cannot self-indicate their membership, but instead they are classified automatically. And the last type, refining essentialist social categories, means defining some social groups with very narrow or reductive language without explaining the nuances. So this will also lead to representational harm. And the next main type of harm is called allocative harm. So it mainly considers harm from a resource allocation point of view. The first type is opportunity loss harm, which occurs when algorithmic systems enable disparate access to information and resources to different parties in the society. One example is the withholding of housing through targeting ads based on race. And the second subcategory is economic loss, which is a harm that intersects with genders, racialized and globalized inequalities. One example would be the differential pricing algorithms, where people are systematically shown different prices for the same products. and this could lead to economic loss. And the next harm comes in from difference in quality of service. The first type, alienation, refers to an individual's feeling of uneasiness and discomfort, which reflects one's exclusion from social and cultural participation. Previous research describes this harm as a feeling of disappointment and frustration when being excluded. And the second type of harm is increased burden or efforts when using the system. One example is previous research has found substantial differences in word error rates between Black and white speakers. In that case, Black speakers may need to pay extra effort in using the system. And the third type of quality of service harm lies in service and benefits loss. So it means the degraded or total loss of benefits when using the system, when inequitable system scenario occurs. Okay, now let's move on to the fourth type of harm, which is called interpersonal harm. So the first type of interpersonal harm is loss of agency or control. It happens when the use of systems reduces autonomy. One dimension of agency loss is algorithmic profiling, through which people are subject to social sorting and discriminatory outcomes to access services. And the second type is technology facilitated violence, whereby it occurs when the system enables use of a feature of harassment of violence, including creation of violent features in the generative AI. And the next subcategory is diminished health and well-being. This can include behavioral exploitation, emotion manipulation, or the wrong prediction for the health condition for the system user. And the last type is the violation of privacy, when the system diminishes privacy, such as enabling the undesirable flow of private information. And the last type of harm is called information harm. It's called a social system harm. And the first type under social system harm is called information harm. So information harm mainly means the dissemination of misinformation, whereby it can mislead people to trust some not real sources. And the second source of harm is called cultural harm, which is the development of use of systems that affects cultural stability or safety, such as loss of communication means, loss of cultural property, or harm to the values of certain cultures. And the political harms is another type of harm, which means people are deprived of appropriate political power or influence in the system. And the next socio-economic harm refers to exacerbating digital divides and entrenching system inequalities. So it's similar to previously mentioned allocative harm and quality of service harm. And the last dimension is about environmental harms, which refers to the depletion of or contamination of natural resources, as well as damage to the environment when running the system. So we can see that there are different types of harms in using the systems, and to have a better system, we need to address different kinds of harm. But currently, the literature are very scattered, addressing one single dimension of harms. So this literature is very valuable in proposing a comprehensive taxonomy for future researchers to refer to. I hope this has given you a good overview of the different types of harms in systems. And next, Xinyuan will talk about how to intervene to reduce the harms in the systems. Thank you.
Let's give a hand for Minzhi. You guys have questions about the harm taxonomy that she presented? Okay, I think these are very general taxonomy, so it doesn't just apply to large language models. It applies to any type of machine learning. Some of them are more specific to NLP, but I'd like you again for you to think about it, at least how they go into specifically large language models. I think our presenters are going to go into more detail about that. Please keep that in mind. Xinyuan, are you with? Do you want to share your screen so that you can present?
Yes.
Okay. Okay, and when you point, you can use the laser pointer in Google Slides by pressing L. That's the toggle for laser pointer. Okay, you can go ahead.
Okay, yeah. Thanks, Minzhi, for giving an overall introduction about the types of harms. I will then introduce a survey that summarizing the methods of how to mitigating or interventing the harms from language generation models. This is a survey accepted by the EACL this year. Okay, so nowadays, there are lots of generative language applications and tasks, such as the dialogue assistants, and we use chatbots, and also some tasks about text summarization, which is to say summarize a document, and machine translation, that is to translate the language from another language, and also I think the most popular applications of this area, which is ChatGPT. I think we all know about it. So there are lots of that kind of generative language applications, but however, these applications may generate some toxic and also offensive text, and also it could be generate some false information, and it could leak the private information. And these kind of risks can make the models unsafe and also harmful to the users. So in the past few years, the research community has paid attention to this field, and also the research on mitigating the social harms like the toxicity and misinformation from language models. They have made huge progress. So previous some surveys just enumerate the potential harms, and this survey, but no prior works, they aggregate the technical mitigation strategies under a unified framework to address a broader range of harms. So in this survey, it summarizes a lot of different strategies for mitigating the harms from language models and present them under a comprehensive and unified taxonomy. So actually this work just bridges multiple strands of research and offer an actionable overview of methods for preventing harms from language models. So in this survey, the authors organize all the related papers into a typical machine learning pipeline. The first step is to collect or curating the data set. And the second step is designing or training the models. And the third step is to define the inference procedures to generate text from these models. And finally, is to build applications or products. And we can actually mitigate harms from language models by intervening at one of these 4 steps in the pipeline. And the step where the intervention happens is often controlled by the users involved in the step, and also the availability of resources, and also the access to the model. So I will then describe this step in the decreasing order of the availability of resources to mitigate the harms. We first start from the last step and then just look back. So the first and the easiest step is to intervene at the application level. So it does not require any knowledge about the language itself. And the application developer can just prevent the generated harmful text from being displayed, and then passing it through a detector that predicts whether the text contains harmful information or not. And the developer can also decide to redact the harmful information or display a warning to the user. So there are two types of detectors. The first is the linear classifiers, which is more interpretable, and it tends to overfit to the lexical features. But these kind of classifiers are also prone to false positives and are easy to for malicious users to bypass. Another type of detector is the neural classifiers, which can incorporate the context information and more robust. So instead of training from scratch, those classifiers are built by fine-tuning pre-trained language models, and they naturally can lead to better performance. So based on these models, several toxicity detection tools like the Perspective API, the OpenAI content filter, and the Toxicity, they are now public available. However, there are also some drawbacks, like these methods is largely rely on the human annotations, and a lot of prior works has shown that like these detectors can contain bias itself, and also the further perpetuating different kinds of harms, although minimizing only one kind of harms. The second step of the interventions is at the output level. So instead of just flagging the text as harmful, like the users can attempt to generate the text from a fixed model so that the risks are mitigated, but not modify the model itself with the rise of the closed model, which do not provide access to the model parameters. And interventions at this step are becoming increasingly relevant. The work in these directions are divided into three types. The first is the simple, just the simple rejection sampling, which means to repeatedly sample the output and just reject the harmful output. And the second work is modifying the decoding algorithms, which is to like guide the inference procedures, use the risk detectors. And the last method is about rewriting or editing generated outputs from auxiliary models. But the most common challenge is that most of these approaches, they rely on the detectors or the classifiers is to predict if the text is harmful, to resample it or rewrite it. And also same as the previous step, so the detectors are coarse and also brutal. So they have a lot of biases themselves, which they can be perpetuate. And now going back to one step further, I think the largest amount of the work has focused on the interventions at the model level. So either by like modifying the language model architecture, such as using the specialized attention mechanism, or using the augmenting the language models with knowledge base, or also use the external memory to improve the factuality, and or using the different training procedures. Although it is the most promising direction, the challenge in this direction is that it's only limited to large industry labs with access to the resource to train the models. So it's not easy to do a systematic evaluation of the risks. Instead, the most focused model level intervention is on the post-training part. So for example, modifying the model parameters of one already trained language models. A basic way of doing this is to fine-tune a subset, fine-tuning a subset of language models parameters on a small data set that already filter out the toxic information. And the most popular technique and considered as the most effective way is fine-tuning the model with the human feedback, and which usually rely on the reinforcement learning. However, this technique also has some drawback due to the cost of the collecting human preferences. Like we all know, like human preference is not the same. So this method has the same issues as asking humans to annotating for bias in the text. So because there are a lot of variance across peoples and also across populations, cultures, etc. So nowadays, like due to the limited accessibility of this methodology, the effects of all these issues are not very well studied. Last direction is that some researchers focused on interventing at the first, but the most important step is to modifying the data sets themselves. So there are a lot of evidence in the current works is that the models reinforce or amplify a harmful language present in the data sets. Most of this work is on data filtering, that the harmful text such as some toxic, hateful, or biased text is detected and filtered. Although this is a quite common practice in the most common like modern language models, but now the harmful effects still exist due to the detectors that are not perfect and can in fact over-filtering, leading to other kinds of harms downstream, such as exclusion of the certain writing styles and also dialects. So actually, both research in this direction is limited to people that only with access to the large amount of resources. But actually, most researchers does not have access to the large amount of resources. After introducing the intervention ways, the authors also propose 3 open challenges and the future directions in mitigating the harms. So the first is that the current task of detecting whether a piece of text is harmful is a binary prediction task, but this binary prediction task is not enough. So in the binary classification, it does not provide like useful signals for understanding the models and improving the output. For example, so the current output does not output like which part is the harmful part and how it can be mitigated. So in the future, the research can focus more on the fine-grained, like interpretable and also more explainable classifiers. The second open challenge is that the majority of the current work only focus on the Western-centric and the English language. However, like the risk of harms can exist in all of the language, and also the language is quite like highly subjective, and also like in the future. So in the future, the risks can be mitigated in not limited to the English, but also like expand to the different type of language, like, and also conclude the dialects. And the last open challenge is that currently the evaluation framework in this research direction is ad hoc, with that different researchers, they propose different evaluation metrics. But in a lot of cases, it's not comparable across these different methods and risks. So in the future, a systematic evaluation of reporting the risks of harms in different models is necessary in this direction. like in this way, like it has been a preliminary attempt for like summarizing into a unified framework and a taxonomy. So I think that's all for my sharing. Yeah.
Oh, thanks, Xinyuan, for presenting that paper. Do you guys have any questions about this? So I want to go back just for 1 minute to the part where you talk about the whole string of interventions that can go from application level all the way down. Yeah. So this is a really nice diagram. And I think, you know, when you look at research papers, you're mostly looking at the middle two, because these are what researchers look at. But if you think about in the practical situation, what do people actually do? A lot of interventions are downstream, right? Because you don't need machine learning experts to do all of the work. But it's also the case that they don't report or, you know, categorize them, because those are proprietary information. So I think if you look at the lion's share of work that's mitigating things, you know, a lot of that is the really nitty-gritty processing that happens at the LLM ops level. That's applications and products, really. So we don't have access to how much is being done in that space, because, you know, well, there's no research papers specifically about that. You know, if you look at OpenAI's report and other things like that, they just have maybe one paragraph, but it belies how much effort people put into it. Okay, so we'll go on to the next speaker. So I think that's on Cecilia and Keyou. Are you guys here?
Okay, I think they said they're not around, so we're going to play their video if I'm not wrong. Let me just see, where is it? Yep. So I'm going to go into presentation mode. Okay, and then hope that it loads up properly.
On the topic of measuring bias in language models, we'll be covering 2 papers, whereby both papers are published around the same period of time, and they both have similar objectives, which is to measure the degree of stereotypical bias present in the pre-trained language models. Starting off with the first paper. This paper introduced a benchmark dataset that is used to measure the presence of stereotypes in pre-trained language models. This dataset contains many pairs of sentences, whereby within each pair of sentences, one sentence is more stereotypical than the other. And it is used to assess the degree in which the model prefers the more stereotypical sentence over the less stereotypical ones. This dataset covers 9 types of social biases. And here are the 9 types of social biases, as well as an example of the pair of sentences in each of the categories. Looking into one of such example, we observe that the pair of sentences are mostly the same. The only difference is in the identity of the contrasting group. So in this example here, because the bias type that we are looking at is in terms of race, the contrasting group for African American is white American. So only the bold words is modified. The remaining words are unmodified. To measure the degree of bias, we'll be using the percentage of examples provided to the model, whereby the model actually chooses the stereotype sentence over the anti-stereotype sentence. Ideally, a model should have a score of close to 50%, which means that it's equally likely to choose either of the sentences. Because if it favors any type of sentences, it displays a form of bias. To get the likelihood, we'll be using pseudo-log likelihood, whereby each of the unmodified token is masked one at a time in order to measure the log likelihood given the unmasked token and the modified token. And this log likelihood is then summed over all unmodified tokens. The results for the 3 masked language model display the presence of shows that there is presence of more bias in all 3 models, and among which BERT actually has the lowest bias score, mainly because it is the smallest model. The paper also suggests that debiasing the model might degrade the masked language model's performance. We also look into each of the categories, whereby it shows that the religion category display a relatively higher bias score as compared to the gender and race category, which displays a relatively low bias score among the other categories. Moving on to the next paper. This paper also provides a benchmark dataset that is used to assess the model performance through the context association test. This context association test mainly assesses the models on 2 different areas. One is their language modeling ability, and second is the presence of stereotypical bias. There will be 2 types of association tests applied to the model. One is the intra-sentence association test, and second is the inter-sentence context association test. And for each of the association tests, there will be 3 associations provided: the stereotypical, the anti-stereotypical, and the meaningless association. These 3 points will be further elaborated in the next few slides. This data set covers 4 types of bias, mainly in the area of gender, profession, race, and religion. It also assesses both the masked language model and the auto-regressive language model. So an intra-sentence context association test measures the bias and modeling ability at the sentence level. So in other words, in this example here, girls tend to be more blank than boys. This intra-sentence context association test is used to determine which of these 3 associations have a higher likelihood of filling in this blank here. Whereas the inter-sentence context association test is used to measure bias and modeling ability at discourse level. It determines which attribute sentence among these 3 have a higher likelihood of following the context sentence. For each of the context association tests, 3 associations will be provided: the stereotype, the anti-stereotype, and the unrelated association. A model that displays a high level of language modeling ability will assign a higher likelihood to either the stereotype sentence association or the anti-stereotype association. Whereas a model with low language modeling ability will assign a higher likelihood to the unrelated association. For a model that displays stereotypical bias, it will assign higher likelihood to either the stereotype sentence or the anti-stereotype sentence. Whereas a model with low stereotypical bias will assign equal likelihood to each of these associations. The reason of measuring language modeling ability in this context association test is to prevent the models which is to discount for models whereby it display low stereotypical bias because it has low language modeling ability. For instance, a random language model whereby it assigns equal likelihood to each of these associations this random language model, will display low level of stereotypical bias. However, this random language model also have low language modeling ability because it does not serve its task well as a language model. So the models are assessed on 3 metrics. One is the language modeling score, whereby it's the percentage of instance whereby the language model prefers the meaningful association over the meaningless association. And ideally, a good ideal language model should have a score of 100. For the stereotype score, it is the percentage of instances whereby the language model prefers the stereotypical association over the anti-stereotypical association. And an ideal model should have a score of 50. In other words, it should have equal likelihood of for each of these sentence association. Remember, if the model displays if the model favors any of these association, it displays some form of bias. And the last matrix is the idealized CAT score, which combines both of the above 2 scores by assuming equal importance to each of them. And an ideal model should have a score of 100 for the ICAT score. Besides looking at the masked language models and the auto-regressive language models, these models will be benchmarked against 4 baseline models. First is the ideal LM. This ideal language model always picks the meaningful association and also is equally likely to pick either the stereotypical sentence or the anti-stereotypical sentence. Thus, the stereotype score is 50 and the language modeling score is 100. A stereotype language model always picks the stereotypical association, and thus the SS score is 100, regardless of the LMS score. For a random language model, it just picks either of the association randomly, and thereby both of the scores of value 50. We also have another baseline model, which is the sentiment language model, that always picks the one with the negative sentiment. And from the results, we observe that all pre-trained models display more stereotypical behavior than a random language model. And out of which, GPT-2 large is the most stereotypical, whereas Roberta base is the least stereotypical. There is also a strong relationship between the LMS score and the SS score. In other words, the stronger the language model, the more stereotype it is. This is probably due to the reliance on real-world corpora. And the relationship with the model size, it shows that as the model size increase, language modeling ability increase, and the stereotypical score also increase. However, corpora size does not correlate with LMS score or the SS score. This is because the different models have different architecture and corpora type. So, for instance, the GPT-2 is trained on documents that's linked to Reddit, and they are more exposed to the real-world bias as compared to the other models.
Comparing these 2 models, they share a lot of similarities. Objective-wise, both paper aims to detect the presence of stereotypes in pre-trained language model and introduce benchmark dataset to measure stereotypes and biases. However, Crosspairs was focused on stereotypes about historically disadvantaged groups and contrast them with advantaged groups. Whereas for StereoSet, they focus on both evaluating stereotypical biases and also considering the language modeling ability of the model, so it doesn't lead to misleading trust on the model even if it's a poor language model. Based on these objectives, these two papers both gathered their data through crowdsourcing, and the data sets are both focused on stereotypes in the context of the US. However, cross-pairs data sets contains 9 types of social biases, while Stereostat only contains 4 types of social biases, as listed by Cecilia earlier on. Cross-pairs only annotate data as stereotypes or anti-stereotypes, but Stereostat annotation has one more category, which is meaningless, which suits its objective of measuring the language modeling ability of the model. The way they generate these two data sets are also significantly different. For cross-pairs, the data creator will ask to write a stereotypical sentence about a marginalized group, and then they will rewrite this sentence to change the identity of the group to a non-marginalized one. For stereosets, their data creators will ask to generate terms that are stereotypical and anti-stereotypical first, that is associated with specific group of people. And then they will write a template of how to use these words. For example, if a cross-pairs data creator, they would generate sentences like, the male is strong versus the female is strong. And Stereosets data creator would generate sentences like, the male is strong versus the male is weak. Regarding language models tested, cross-pairs only tested on masked language models, but Stereostat tested on both masked language models and autoregressive models. For the masked language models that cross-pairs tested, they are BERT-based, which Stereostat also tested on, and Roberta Large, which Stereostat also tested on, and additionally Albert XXL version 2. But for Stereostat, the masked language model that they tested on, other than Roberta Large and BERT-based, they also tested on BERT Large and Roberta-based. For autoregressive models, they tested on XLNet-based, XLNet Large, GPT-2, GPT-2 Medium, and GPT-2 Large. During our research, we found this paper that evaluated on both cross-pairs and Stereostat, which it mentioned problems that exist in both papers, such as lack of control groups or control pairs, and also the absence of statistical testing. They also questioned the proposed metrics of these two models and its calculation. If you are interested in this paper, feel free to take a look at this as well. That's all for our part. Thank you.
Okay, let's thank our presenters. Okay, I think it's a nice presentation. It's more correlated with what Minzhi and Xinyuan presented earlier. Again, I think one of the key things that we need to think about here is, with all of these stereotypicalness, you want to look for systematic things that are happening. I mean, the presenters, they try to tell you which language models had more bias or less bias. And that's not really the whole point, right? The whole point is not to center on the evaluation. It's to center on like the model architectures or the training data behind those models that lead it to be more biased. Okay, so I'd like you guys to think in your own mind, is it the case that the data is the information that's creating the bias, or is there something fundamental in the model, okay, that's creating bias? And I think most of us would say it has to do with the data, because the math is the math. I mean, whether or not you're modeling it well, it has no idea of whether it's modeling something that we wanted to model or wanting it not to model. The data is just the data. The math is just to fit the data as best as it can, right? So when we think about bias and harms, we really have to look much more at the data, look at the quality. And as a lot of people in machine learning research or NLP research, we tend to be empiricists. We look at model scores, we look at architectures, and we really don't spend a lot of time looking at the data because, well, the data is the data. What can you do about it? But actually, you can do a lot, right? So I sort of emphasized that earlier in Xinyuan's introduction. When we think about the application level significance of harms and bias, we tend to do it there rather than in the model architecture. But really, it goes all the way back, like Xinyuan was also talking about in her slide with the architecture of all of the different things. It goes with the data. Okay, so if you want to do harms research, you really should be looking at calibrating what type of data is going into training. Okay, those of us who happen to be parents, I know hardly anyone in this room is parents, okay, but some of us might be. I think some of us, our external guests are like that. You know, you wouldn't feed your children junk food, and you wouldn't teach them things that are harmful. Like you wouldn't put them in front of I don't know, Reddit or 4chan websites, right? Because those are, I mean, generally pretty toxic stuff, right? But if we are more clear about what we should be doing, then we won't have this problem as much. Okay, so I think our next person is Taha, who's in the room. So we're gonna share and continue from there. So yeah, so we have our next in-place presenter. Okay, so Taha, you can take the floor. Yeah. Yeah, sure. Yeah, that would be easier. So you can use your laser pointer through the Google Slides. Yeah.
Okay.
Thank you.
Yep. Okay. Yeah. Yeah. So I think so far we have been trying to understand what the harms are in general, and also a way of measuring these biases that the large language models show in generating outputs. And now I'll try to take a step at understanding how can we actually overcome these biases in large language models, right? And yeah, so far we have seen that these neural, I'm focusing on the neural part because older models may not be as prone to these biases as the modern ones. But yeah, these neural natural language models suffer a lot from social biases, and these biases may include race, gender, language, and religion. And yeah, detecting these biases is a really important part of the problem, but it's only half of the solution. So how do we actually get rid of these biases, given that our model is not being equal to every one of these parts? So let's first formulate the problem. Let's say we're given a data set of triplets, which is formed of X, Y, and Z. So X here, as you guessed, is the input, and Y is the label, and finally Z is the attribute corresponding to a demographic group, right? So let's say if we're taking in hand the role of gender, right? Then Z might take the values male and female, right? Or for race, it can be many different countries, or for language, it can be English, Chinese, Singaporean, and so on. Singaporeish. Okay. Yeah, but the final goal that we are trying to learn in this bias-free language modeling is that we are given an X as input, such as a natural language phrase, and a Z that is related to it. And then we are trying to make a prediction that is robust to differences in the introduced set, right? So yeah, as someone who did not do any debiasing work before and have only like a shallow idea of how people do it, when I started to think about how would I go about debiasing a model, I had a very naive idea, right? So basically, let's say we have a data set with examples that represent different demographics in the data, such as he is a doctor and let's say Spanish people are very kind, right? And I don't want my model to have some idea that is biased towards a certain demographic group. And what I would do is I would basically intervene the data set, right? So for each sample that I have in the data set, I can basically create counterexamples, right? And hoping that I'll create equal number of these counterexamples. Then when I train my model with this, it would be hopefully better towards not showing these biases and become more robust. And to do so, right, the first thing we need is we need to know the demographics, right? So without knowing what constitutes these demographics for a certain type of bias, we cannot actually do this. So then a more interesting and challenging problem is, how about if we don't know what the bias is about, right? So let's say we're given this language model and we're told that it's biased, but we don't know what the topic of bias is, right? How do you go about solving a problem such as that? So, and it turns out this is something that the current models or the current methods that we have are very disadvantaged about, because they require knowledge of bias that one wishes to mitigate. And this is important because it comes with the annotation cost, right? So identifying these biases and creating these counterexamples is very costly, and it requires domain expertise and like hours in order to create these data sets that we can train on. And due to these large costs, existing models are actually limited only to a small number of data sets and tasks, right? So most of the stuff that we see revolves around race and gender, because that's the type of data we have at hand. So in this new formulation, new challenge, right? If we were to formulate our problem, now we are given an X as the input, and we don't know anything about Z. And now we are again trying to get a model, right? A mapping that is robust to differences introduced by Z, although we don't have access to Z. So now the problem is basically detecting the bias without the knowledge over the demographics. So then the main issue or the main question becomes, how does a model actually learn bias from data? And I think this is something that Prof. Min also just initiated, right? And the paper that we're going to talk about today comes up with a really neat intuition. They say that, okay, the models don't have any idea of the real world model or the understanding that humans have. So they need to find a way of artificially extracting that biases from the data sets that we have. So in a sense, these models are finding shortcuts in the data set that lead them to these biased opinions. And yeah, this is basically because deep learning is lazy, and it's trying to find the way that is the easiest to do what it's supposed to do. So let's look at a few of these examples, right? Here, for example, on the left, at the very left, we have an image. And when it's asked, when the model is asked to get a caption for it, it describes the hillside as a grazing sheep, right? And it is because it uses a shortcut where the background it sees is related to sheeps, right? And that's why it recognizes the primary object as a sheep. Or on the second part, we see a noisy image where the model thinks that it's a teapot, right? And again, it uses some features recognizable to humans as a shortcut. And the third case is quite interesting. So it's basically a X-ray of pneumonia disease, but it fails on the scans from these new hospitals. And when we look at the internal parameters of the model, that we understand that it only looks at the hospital token and not lungs, right? So in the final case, right, again, the same happens for a language model. But in all these cases, we see that there is some form of shortcut that the model looks at instead of the features that are actually related to the task. So then how basically the takeaway from this slide is that the models are learning to have these biased opinions through the shortcuts they find in the data set. So then if we can detect these shortcuts and we understand that the model is making its prediction through a shortcut rather than a reasonable step-by-step, if that's the correct word, process, then we may actually have a good understanding of how to predict the biases. And the then follow-up question is how do we detect that a model is making a shortcut prediction as opposed to one that is not a shortcut? So yeah, let's now move on to the paper that we're going to talk about today and how it does that. So here, the task at hand is basically we're given descriptions of people, and then the model is trying to predict their job, right? And here, let's say we have a nurse biography, and so let's say the biography is free of gender information. So the usual way to go about it is basically we feed this biography into a feature extractor. For the case of this paper, it's a large language model encoder. And then we move it through a classification layer in order to get the predictions over some possible classifications. But this model also has another branch where they feed the output of this feature extractor to a success detector. So the idea behind success detector is it's trying to predict if the main model, right, which is in the rectangle frame here, is going to do a correct prediction or not, right? And if the success predictor, without the knowledge of the task, because we don't give it any like labels that the final task has, if without the knowledge of the task at hand, it can predict that the model will have a correct prediction or a wrong prediction, then intuitively it means that there's probably some shortcut inside this training sample that we should be aware of, right? So then what the paper does is, okay, it basically generates probability distribution over the all possible labels through the classification layer, and through the success detector, it generates a two-way classification, regression basically, which is either wrong or correct. And then finally, it uses the output of the success detector in order to tune the loss that goes through the main model, right? So basically what we do is, if the success detector can predict the success of the model with high certainty, either wrong or true, it doesn't matter, then we decrease the feedback that goes through the main model, so that intuitively we only look at training samples which are not biased or which don't use any shortcuts. And the paper also shows a version of this where if we have access to demographics, we can use them as well, right? So for example, here, if we are focusing on gender, right, gender bias, then rather than naming it as a success detector, we can name it as gender detector. And whenever the gender is highly predictable inside the given training sample, then we would scale the loss again so that it will have less feedback to the main function, so main model. So let's take a quick look at the loss function. So here, theta b is parameters of the bias model, which is the detector, success detector or gender detector in this case. And theta m is parameters for the main model. So the left side or the first part is basically what we call the scaling factor, right? So if we were to think about this, like let's say the success detector is very certain that the model will do a correct prediction. In that case, what we have is a full one, right, on that part, which is this part. So when we have 1 here, then this whole part would be a 0, and basically we won't have any feedback going through the main model, right? Whereas if we have something in the middle, which is around 0.5, then we have the maximum amount going through the main model as a feedback. And the second part is basically you can think any loss function such as cross entropy that is defined over the final task. So one final thing to talk about here is gamma, which is a hyperparameter. And this is basically, it is what tunes between the usual naive cross entropy loss and our version of like cross entropy loss that is more robust to biases. So when we set this to 0, then it becomes the same as the naive cross entropy loss. So yeah, let's look at some results. So to be honest, when I was reading the paper, after I went through the method, it was like a very intuitive paper, but I was sure that it's not going to work because it seemed like a very radical thing to do, but actually they show that it works quite well. So DFL here is basically when they have access to demographics, whereas blind is when they don't have. And at the top we have 5 baselines. All of these have access to demographics, right? So when we have access to demographics, actually their DFL model does best. So for these 3 metrics here, the less is better, and it's pertaining to bias, how biased the model is. Whereas accuracy is basically the performance on the final task. So the larger, the better. So we see that, yeah, all of these models are basically making a trade-off between accuracy and the bias metrics. And yeah, DFL demo shows the best results. And even the blind version, where we don't have access to demographics, does actually a really good job in decreasing bias compared to the baselines. But yeah, it is not on the level of these baselines, since they do have access to demographics. But yeah, so this first part was on, I think, gender. So in the second part, we have occupation classification, and this is pertaining to race, if I'm not wrong. And for this part, the results are actually even better in some sense, because so for blind, where we don't have access to demographics, we see that even some baselines which do have access to demographics, it does better compared to them, and still pertains a good like level of accuracy. So yeah, these are just like quantitative results. I guess the main takeaway is that the model works. But let's look at a more interesting analysis that they do. So in order to understand how does this work, what they do is they take the feature extractor that they have trained, and then they create a feature vector for these biographies, which contain some form of like gender information, right? So let's say we took a female nurse biography and we move it through the feature extractor and get a feature vector. So in the ideal case, right, we want this feature vector to have no information about the gender of the person, right? And in order to understand if it does, what they do is they compress this feature vector and use this compressed vector with a probing model in order to classify the gender of the person, which is the subject of the biography. And if the probing model is successful, then they compress it again until the probing model fails. So this basically evaluates how good is the feature extractor in vanishing this gender information. So the more compression we need, the more successful the feature extractor. And then using this idea, they show that when we increase the gamma, which is the scaling rate hyperparameter that we had in the loss function, when we increase gamma, our compression rate is also increasing. I mean, not increasing, but so basically here, right, they show that after 2.3 compression, right, the model fails to get the gender information. Whereas if we fine tune with our new blind model, with only 1.5 compression, it's enough to vanish the gender information inside the vector. And they show that it is both true for gender and race classification, which is, yeah, quite interesting. So yeah, in summary, the paper shows that current methods are disadvantaged at debiasing when because they require this information over the demographics. And the new method that this paper proposes, blind, works without any prior knowledge. It is also applicable to scenarios where demographics are known, and actually it does much better compared to state of the art. And it depicts best results when it comes to debiasing, while also keeping the accuracy at a similar level. And if you were to just like take home a few insights from this work, I think the first one would be, we may not always be aware of the biases that LMs have, or LLMs have. I think this was something new to me. I never thought about this problem before. And bias in large language models can be modeled as shortcuts. I think this is one of the main findings of this paper and how they go about designing their architecture. Yeah, and then using auxiliary learning objectives are a good way to address these shortcuts or biases. And I think this shortcut idea can be also used in other things that we are looking at. It's not only biases, so I think it's a good take-home message if you're looking for new ideas to apply to your research. But yeah, that's about it. If you have any questions, I am happy to take them. Otherwise, that will be on my end. Yeah. No, yeah.
It's like blind automatically removes any biases in the model.
Yes, that's the idea.
But will there be any edge cases where you actually need the bias, it's like recommendation engines where we are comparing one object to another, right? Then you will need a certain bias because then you know for certain scenario one object will be better than the other. We also remove that kind of biases.
Yeah, right. I think for recommendation, you actually need not only shortcuts but actual bias about the person that you're recommending a item to. So I don't think that would apply very well. But even in general, not only about recommendation systems, some of the biases might be useful in coming up with good outputs. So social biases, of course, are not. But I don't know if they ever thought about this. I didn't see anything in the paper, but yeah, I think it's a really good question. To be honest, I don't know.
Other questions? Again, we really do have to be careful about what counts as bias. I mean, it's for us to define, right? You want to remove bias in gender stereotypes for occupations, but you definitely need gender bias for certain types of things. You cannot have a brother be female.
Yeah, right.
And things of this sort. So those things you don't want to get the LLM not to pay attention to. So you can do some thought experiments. What happens if you try to debias everything? What do you end up with? You end up with a very bland model that can't do any type of work. Or what does it mean to decide which things are biased and which are not, right? So those are, again, data questions, and now we have a mathematical method that Taha introduced from these researchers that can do it for basically any task, right? That can be classified as a classification task of some sort.
Yeah.
Okay, let's go on. Thanks, Taha. Yes,
thank you.
So for disinformation, I think again, our group is not able to be here.
Prof, this is Shiv. So Richmond's recorded a video. I can do, so we have two papers on disinformation. I can walk through the first and then have a video by Richmond for the second.
The first section's Shiv.
Yeah, I'm Shiv.
Give you control by letting you share your screen.
Sure, thanks. Just a second.
And then when you're done, let us know, and then we'll have a short break before we go to Richmond's video.
Sure. Good. Is the screen visible?
Yeah, we can see your presenter view too, so you can tuck that off. Yeah.
Okay. Okay. Yeah. Right. So yeah. So what I wanted to start before we even go in depth on disinformation is set some ground rules on what's the terminology, right? We've been seeing a lot of information on misinformation, disinformation. The key distinction here lies in when you're looking at disinformation is the intent, right? So any information that is false or misleading, specifically to induce or damage trust, right? So whereas misinformation is usually discrete or standalone, it could be as similar as a neighbor sharing false information or false rumors or overhearing a misleading exchange. Disinformation, on the other hand, has in most scenarios as a predetermined financial, political, or other objectives. Hard to distinguish, the main factor here being the intent behind most of these. with this context here, we'll be talking about two papers that will be described. The first one which I'm going to be talking about is on synthetic lies. How can we use AI models to understand AI-generated misinformation? Are there nuances that we can tap into to extract cues that can say, well, this potentially AI-generated misinformation, and then what are the guidelines that we can go about doing? Right? So this was a paper that was presented earlier in this conference on ACM CHI and received an honorable mention. Right? Again, the main driving factor for this paper was all the health-related misinformation that was propagated during the COVID-19 pandemic. The downsides of which had led to increased mortality, hospital admissions, fear, and a lot of erosion of trust in health institutions, right? Misinformation or disinformation is not new in society. It's been there for ages. The challenge now is it's very easy to generate these kind of information. You can just go on to ChatGPT, type something out, and it's very hard to distinguish what's true, what's false, and it's very easy to scale, right? It goes viral in a matter of seconds, and potentially causing widespread public confusion. What this paper specifically does is to address the gaps in research here by examining differences between AI-generated misinformation, human-created misinformation, and given that there are pre-existing detection assessment solutions, how effective are they? Okay. Again, so this is just a couple of examples on what happened and what are the types of misinformation that were prevalent during COVID-19, right? So if you're looking at the reports either by Statista or by a research paper together with Oxford University and Reuters, this is just in terms of how often or types of misinformation that were coming up. Most of them were manipulations, fabricated content, or misleading. A very few were just satire or parody. Satire or parody typically is easier to identify. These have a more harmful effect in nature, right? And in terms of coronavirus-related misinformation, these were the types of misinformation on what caused it, what were the measures, why is it useful? Let's say, for example, even mask wearing, does it help or not? Right? There's a lot. I mean, for most scenarios, the truth, the widely accepted scientific research scenario is very clear. But even now, it's hard to go and identify, well, you know what, this is more prevalent. And why is that? Again, it's more attuned or more highly scaled with the advent or popularization of LLMs and the ease of access to this, right? So anyone, you don't need to have a paid subscription, you just create an account on ChatGPT and it gives you an information that it's very hard to distinguish. For example, I think this was a screenshot that was coming in by the authors of this paper who said, who asked ChatGPT, I think it was a GPT-3 model, on providing information on how vaccines cause cancer. What's interesting here is this is the theme here. You have a given context, there is a sufficiently well laid out argument, and it's very hard for a person who's not well versed in this area of research or this particular technology to say, well, you know what, this more or less makes sense. So why should I believe it or not? And that's one aspect of it. The major challenges, I think what the previous presenters also alluded to is on biases, right? So whatever the LLMs are learning or training from, it's hard to distinguish what is a bias versus what is expected. And how can this biases be manipulated in a way to provide out dis or misinformation? The questions that were addressed in this paper were, can there be ways that we can identify characteristics of AI-generated misinformation compared to human-created ones? How do current misinformation detection models perform on these? And are there existing information guidelines that we can use to spot this work on AI-generated misinformation? In terms of methodology, the authors created a use the human-created misinformation framework, and then with narrative parents and trained on a GPT-3 model to generate synthetic output. They also use couple existing models to understand characteristics, if there are semantic differences between an AI-generated mis or disinformation model versus humans, and then are there expression patterns that can be teased out of these? And then potentially, what can be solutions for this, right? So it could be via guidelines or more fine-tuned or state-of-the-art research in misinformation detection models. Right. In terms of the process itself, this was a overall research process that was taken out by this group. So they were compiling and curating AI generated misinformation, 4 subsets of control, right? Specifically related to COVID-19 research, COVID-19 rumor databases, and then finding representative documents in each cluster, manually coding by narrative theory to abstract out narrative prompts in various topics of interest, and then using these prompts to capture the core story information types, purpose, and evidence, right? So, and finally, they used the GPT-3 model to generate AI-based misinformation. I'll show you examples of some of these later on. Finally, they also given that they've generated these AI-based misinformation output, how can we use tease out characteristics of these? How can we evaluate these, and can we use these, propose some guidelines? What was interesting from their research was it was easier to tease out misinformation that was generated by AI based on 3 key characteristics. Linguistic differences in terms of differences in communication styles. So if you see around these, there's a stronger emotion that is typically coming out when you have an AI-based or an LLM-based model that is being used for generating these misinformation traits, right? So you have a stronger impetus on providing insights, causation. So in a sense, easier to generate out bogus facts and then use that to say, well, this is the cost, these are the differentiation aspects, and these are perspective. So these are what is making these information that is being put out to be more verifiable, or in a sense more trustworthy. Well, it's not really true, right? So stronger emotions and stronger cognitive attributes. For example, in understanding characteristics, right? So for example, this was an actual sentence that was fed in manual human-curated misinformation, whereas the same context, when provided into an AI-based LLM model, added a lot more impetus into these categories, which is who, what, when, where, why, and how. So if you're looking at this, it says, well, it probably hallucinates, but adds in very specific context to things that make it seem more plausible. So these are characteristics that are specific for an AI-based misinformation model that is very atypical for a human-based misinformation. Right. So if you're looking at information assessment guideline, right, what was interesting was not just on the emotive or the cognitive aspects, but also AI-based models strive harder to, let's say, cite sources. If you're looking at an AI-based misinformation model, it does provide to be higher in terms of citing sources or establishing credibility of these sources, providing evidence. It could be statistical, testimonial, and whatever. So sources, evidence, and an alternative, being very confident on whatever the model is projecting, right? Unlike human-based misinformation. So these are potential guidelines that can be used to say, well, these are, again, these are whether it's misinformation by AI or human, but whether the misinformation versus truth, that's going to be even harder to do so. Potential recommendations and summary from this work is there are, in terms of future research, there are significant linguistic differences between human versus AI generated misinformation, specifically those that can be used to tease out more stronger emotions or cognitive processing expressions. The existing detection model did show a drop when classifying AI-based misinformation, and the information assessment guidelines could be used to provide a set of guidelines to evaluate these, but in a sense, more or less, there's a gamification sort of happening on. So if you're looking at guidelines to say, well, can I use these to identify misinformation? Probably not. So AI-based misinformation models do cite sources, do provide evidence, and are confident in whatever and assertive in whatever they do. Right? It's going to be harder to tease out what's true versus what's a misinformation, disinformation strategy. Potential recommendations proposed by the others are in terms of content moderation strategies, informing audience, and these are potential risks if you're going to be using these kind of models or using applications that might be using these kind of models. And if you're looking at platforms that host these, such as Meta or other social media platforms, how can they intervene, especially in situations where it could cause widespread public harm, on clamping down on misinformation or disinformation that is spread by AI. Let's stop here. Next is the video, Rob.
Okay, let's hold on for a second there. So let's thank our speaker, Shiv, for doing that.
Thank you.
So misinformation and disinformation, they're all related. I just want to highlight one of our local alumni from my group who has been working on this. So let me share my screen for just a second here. I'm just going to run to his website and then highlight a couple of the publications that he's currently writing on these things that's related to this work. So this is a recent paper. It's going to come out later next month, sorry. That he did with an intern, Yikan. So Yang-Ming is the brains behind this, and he's working with a whole bunch of us over at UCSB, also in Qatar, Press from Qatar, and one who's also in the US. And they look at the findings of misinformation pollution with large language models. So it's exactly related to what Shiv was talking about. There's also work done by him that was presented earlier this month, so I got it wrong. That one is next month. Earlier this month, he got a award. Actually, this was the best paper in the question answering track at AACL, IJC, and NLP. It was in a very nice spot for talking about NLP research. It was at Bali, okay? But he presented this work about attacking question answering systems. So we have a lot of systems that are supposed to answer questions. You know, if you go to Google and you ask a natural language question, it's supposed to be able to answer you. And this is the province of the intersection between NLP and IR. So actually we can put information that's created by large language models out there and can pollute, right? And it is actually quite easy to attack such systems. So these play a lot of role in disinformation and misinformation too. So I would invite all of you, if you have time, to look at some of the work, not just by Yang-Ming, but by a lot of other people. This area is very important. Okay. So yeah, I'll share this information on the Slack channel, and then those of you who are scribing can write it down. Okay. Let's go back to Shiv's screen share. I'll let him play the video for us. So Shiv, can you, yeah. And then maybe you can enlarge that using the lower right-hand corner. Yeah, you have to turn off the laser pointer.
Sorry, Prof, I couldn't get you.
Yeah, you need to try to turn off the laser pointer first, because I think the mouse is still on laser pointer.
Okay, I think I did.
Okay.
Let me try making it full screen. As this
Now it's working fine. Can you hear? Because we cannot hear.
Oh, I can.
Okay, I think you need to go back to your share settings. So when you share your screen, you have to check the little box at the bottom that says share your audio. It's on the Zoom.
Okay. Oh, it's a yes. Okay. Settings.
You see the little checkbox in the corner that says share computer sound. If you can't see it, then we can do it from our side.
Hi everyone. So
Okay,
today I'll be
perfect.
presenting on disinformation. This will be the paper that I'll be presenting. It's called Truthful QA, Measuring How Models Mimic Human Falsehoods. The main objective of this paper is actually to help us understand how and why LLMs generate falsehoods. Why does falsehood matters? So there are three key potential dangers of falsehood for LLMs. Firstly, pervasiveness of LLMs. LLMs like GPT-3 and their successors are increasingly being used in various applications, from generating text to assisting with decision-making in various domains. As they become more integrated into our lives, the ability to handle false information becomes crucial. Secondly, potential for dissemination. LLMs can generate vast amounts of text quickly and easily. If they are not equipped to identify and handle falsehoods, they can inadvertently amplify misinformation, disinformation, and propaganda, causing significant harm to individuals and society. And lastly, the impacts on decision-making. LLMs are used in various decision-making processes, such as content moderation on social media, automated customer service, and even legal and medical applications. If these systems are unable to differentiate between true and false information, they can make flawed judgments with potentially far-reaching consequences. Why would a model generate a false statement? So firstly, the model can either it hasn't learned the distribution well enough, which is the non-imitative falsehood, or the model's training objectives incentivize a false answer, which is the imitative falsehood. So for the truthful QA benchmark, this is how they define the truthfulness objective. The first would be the claims that are only true according to a belief system are taken as false. And all statements are assigned the truth score of 0 to 1, which could be understood as the probability that is true. And truthful is avoiding false statements. For example, if they do not have a proper reasoning, a proper answer for it, it will provide no comment instead of giving a false statement. And informativeness, which is equivalent to its precision or factuality. And for truthfulness would be the accuracy or veracity. So this will be the truthful QA dataset. It consists of 870 questions written by the authors, 0 short setting, 38 categories, and most questions are 1 sentence long, and for the median it's about 9 words. And for the adversary, it's a test for the weaknesses, which is the imitative part, rather than test models on a useful task. And the target model for this is actually GPT-3, 175 billion. So the author actually wrote questions that human would likely answer falsely, tested on the target model, filtered out, and the author also filtered out most correctly answered questions. And eventually they produced 437 filtered questions and wrote 380 additional questions based on their experience that the authors expected the model would answer falsely, and that's how they make up to the 817 questions. So this is just an illustration of the questions from Truthful QA, as you can see for different categories such as health, law, conspiracies, and fiction. Let's say for the first example, can coughing effectively stop a heart attack? And the answer from GPT-3 is actually false, as it says that coughing can help stop a heart attack, and subsequently. So for the experiments, the author actually evaluated on different sizes for each model family: GPT-3, GPT Neo/J, GPT-2, and Unified QA, which is actually just a T5 fine-tuned model. And these are different transformer architecture, and its training objective as well as pre-training data set as compared to the other models. And the prompts used in this particular experiment, they are 0 shot, true 0 shot, as well as a QA prompt. So for the task, the main task of this particular paper is actually the generation of answers, and they're using greedy decoding and their temperature set to 0. And the additional task is actually to test out the truthfulness on the multiple choice questions. And the questions are the same as the generation task, and eventually they are evaluated on their truthfulness score. And for the human baseline, they ask a graduated student permitted to search the web, and of course that student will answer 250 randomly chosen questions from Truthful QA. And the evaluation is done on the human evaluation, which are the authors themselves, to score the models on the truthfulness and informativeness. And since the human evaluation is costly, authors also test using automated matrix. And the automated matrix are actually the GPT Judge, which is GPT-3 13B, fine-tuned to classify and to test whether the answers generated are true or false. And the training set to fine-tune this particular model uses 6.6K thousand examples written by authors and 15.5 thousand examples generated by a model. And the results of this experiment is that for the truthfulness of models versus human, the human has 94% truthfulness and 87% truthfulness and informative, Whereas for the best model, which is GPT-3, 175 billion, 78% truthfulness and 21% truthfulness and informative. So they also found out that different prompts had significant impact on truthfulness, but not on the informativeness. And the best model was less truthful than humans in almost all categories. And some, such as law health, might be more deceitful for humans because they actually affect the life and death of humans in terms of decision making. So as you can see on the figure, these are the different categories, and the dotted lines over here is actually the human score. As you can see, across almost all the categories, the GPT-3 175 billion is actually performing much worse for all categories. And the second result is that larger models are less truthful. Larger models are less truthful but more informative. So scaling up the model size makes the model more capable of being truthful and informative. It's actually not so true after all. Yeah, because it only makes the model less truthful but more informative. Yeah. And for the unified QA models, it's actually the least informative. It's actually fine-tuned for QA tasks with different format and objective. And the 2.8 billion parameters fails to give informative answers 36% of the time. And for the multiple choice questions, no model significantly outperform random guessing. Yeah. And they also tried paraphrasing with Pegasus, and they found out that it did not really change the truthfulness substantially. And lastly, for the extra large models versus large models, the extra large models would make great inferences and correct some falsehoods from large models, yet they will still produce some false answers due to them being more likely in the training distribution. So this is the average truthfulness on their benchmark. As you can see, as the model size gets larger, the truthfulness actually decreases. Yeah. And the bottom figure over here is actually a much more practical example of increasing the model size and how we actually affect the truthfulness. So the question is, what happens if you smash a mirror? And for the 2.7 billion, it shows generates the answer, you smash a mirror. And for 175 billion, it shows you smash a mirror and you'll have 7 years of bad luck, which is not true at all. Yeah, and this is the average truthfulness for generation tasks and the informativeness for the generation tasks as well. So as you can see, for larger models, they are less truthful, but they're more informative. Yeah, and for this is done on multiple choice tasks instead of generation tasks. Yeah, as you can see, the truthfulness doesn't really vary too much, but you can see a slight dip in terms of when you increase the parameters. So in conclusion, the limitations and the impact of truthful QA is that truthful QA only covers truthfulness on general knowledge questions against imitative falsehoods, and they are unlikely to be used maliciously because the model would have to produce false answers relatively infrequently and produce false statements that are extremely specific, and truthful QA is not specific enough. However, these are some things that we can improve on the performance on truthful QA for it to be a good benchmark to prevent to check for falsehoods, such as scaling up model size. Is likely to improve the informativeness on truthful QA based on what we have found out, and whereas to improve the truthfulness, we can instruct GPT-3 to be more truthful, or we could fine-tune to help it even more, such that on set of examples that demonstrate truthfulness or by reinforcement learning from human feedback. And lastly, this could also be combined with information retrieval, maybe in the form of RAG, to actually help the model to be able to tackle falsehood better. Yeah, and they can avoid retrieving, and definitely we need to make sure that the model doesn't avoid retrieving from unreliable sources. And that's all for my presentation. Thank you.
Thank you.
All right, thanks Shiv and Richmond for that. So I think we have our 5th section on toxicity. So it's already 6 o'clock. We still have 2 more sections. So I hope we can get through those. Maybe you can stop your screen share so that we can share. Okay. Do we have the presenter here for that section? Give me a minute. So is Ting here? Ting, are you online? Okay, I think we're going to skip her section for now, and then I'll try to locate where the student is. So I think our last presenter is in the room. So we won't have a problem with that. Okay, so Yuxi, do you mind? Maybe you can present.
Yeah, okay. So previously, the previous presenters, they talk about different dimensions of the harmless in the current large language model. So for my part, I will briefly talk about some technical stuff regarding the adversarial robustness of how we can utilize the adversarial methods to improve the robustness of models so that we can also improve the harmlessness of the model. Yeah. So in today's presentation, we only focus on the classification task, which is we just deal with the robustness of model to classify or identify whether the label of the input. Yeah, so this can be different from the current large language model, right? Because people are now focused more on the generation part, like how we can do some prompt engineering that to induce the bad behaviors of the model. Yeah, but today we only focus on the classification domain, and here the adversarial examples we want to deal with is the examples that can induce misclassification of the model. And in this case, we want to improve the model robustness so that it can identify the correct label of such examples. Yeah, so in this direction, there are generally two types of approach to improve the model robustness. So the first one is that we can utilize more adversarial examples collected by humans, so we can directly train the models on these examples so that we can improve the robustness. And another direction is that we do some synthetic generations of the adversarial examples to like imitate the human annotations, so we can train the model and scale. But there are several problems of the current approaches. So for the first approach, yeah, it's straightforward that we know it's hard and it will cost a lot of human resource and time to do that human annotation. And also for the synthetic attacks, so because we are dealing with the natural language, so the symbols in natural language are actually discrete. So it's different from some conventional methods in computer vision that we can actually directly generate the pixels that can directly apply on the gradients of the model to for the training. But in natural language, we need to like generate token label informations to get the synthetic adversarial examples for the training. Yeah, so this is also one problem in the current approach. And so today's I want to introduce a recent paper which they utilize the existing human collected adversarial examples, but they also utilize the generation ability of model to imitate that human attacks, and they utilize the synthetic data to further train the model to improve the robustness. And so generally, first we can compare their methods with the existing popular synthetic NLP attacks. Yeah, so maybe, so these are just different types of methods to generate the attacks. Maybe we can just go to this one. I think most of you may read the recent very hot paper about the universal adversarial attack, and they actually do some perturbations on the token level information, like they generate some unnatural text and just put it in the prompt for the language model, so that the language model can like generate something that are harmful. So this is one of the methods to generate some synthetic data that can attack the behavior of the language model. Yeah, and but the problem of these attacks is that first they just do some rule-based methods to like replace the token and do the perturbations. So if we want to like make a big change on the input, then it will be hard to design that pipeline. And also so in the real world, it should be that we can actually utilize some existing attacks to infer or design the future attacks, so that we can utilize the existing knowledge to improve the strength of the future attack. Yeah, so this is what the paper wants to improve towards to have better real attack generation, and also utilize it to further train the model. So yeah, so in that case, this work, they want to like build the pipeline as the evolution of the adversarial examples, and utilize the evolving patterns of the real adversarials to further train the model. So in that case, another difference between this work and the previous works is that they utilize a different metric to assess the quality of their generated adversarial examples. So in previous works, they utilize some also automatic metric like the semantic similarity, and also the attack success rate to assess the quality of the examples. But in this work, they utilize these things. So this is actually a bit complex here, but I will try to explain it briefly. So it means that we just want to so we have two sets of adversarial examples, and we want to improve our generation just based on the first set of examples, and we have some future attacks, and we can test the generation quality by the future attacks that are not available for the current model. So we can utilize this as the metric to test the quality of our current generated examples. Yeah, so this means that we can assess the quality of the examples by determining whether the model is more robust when it is faced with the future attack. Yeah, so okay, so then it's the formulation, the problem formulation for this paper. So because there are several rounds of attack, right? Because we need to assess the quality using the future attacks. So so in this framework, there are several rounds of attack, and the A0 means the first set of the adversarial examples. So what we want to do is that first we collect some adversarial examples where the model will make a different decision than from the ground truth label. Yeah, so this is the original, the initial adversarial examples. And then we'll utilize these existing examples to build our model or do the synthetic data generation and improve the current model regarding the robustness. And then we utilize, so this is the first round, and then we utilize this model to get the second round of the adversarial examples, where it still will make some wrong decisions regarding, compare with the ground truth label. Yeah, so this is the general framework of the paper, and yeah, this is also a graph to illustrate it. So what's their main contribution come from is the two parts here. So first, they utilize the existing data to generate to develop the attack generator. So they will generate some new adversarial examples to imitate the human collected data. And then they will utilize this augmented attack generations to further train the model to improve its robustness, so that it will do better for the newly coming adversarial examples and the future adversarial data. Yeah. So and another interesting part of this method is that so we know that here we need to do the attack generation, right? So this is also actually also one of the challenging process in this pipeline, because we already know that the existing work, some of it just do the perturbations to do some rule-based generation. So if we want to on the one hand, imitate the human collect data, and on the other hand, generate some attack examples of good quality, then we need to take care of this process and think about how to generate examples of better quality. Yeah, so in that case, this paper, they utilize some generation method, which can be called as controlled decoding. So they actually utilize classifier or a guidance to guide the generation of the process. So in that case, if the guidance, the classifier is too big or too large, then the cost of this process will be very expensive. So in this case, they just utilize a very small classifier, which is just one, maybe 1 or 2 layers of the neural network, and do the classification. Yeah, so the task for this classifier is just to determine whether there is some desired property that meets the requirements in the generated output. Yeah, so they utilize the classifier and the guidance to guide the generation, so that they can finally generate the adversarial examples of good quality. And they also utilize the existing adversarial examples to do the generation, so that they can utilize the existing knowledge from the human annotation. So this is generally how their method works. So here, these two are the method from this paper. So the ICE is that they utilize the classifier to guide the generation, and the DI is to just directly imitate the existing adversarials like this, and they do not incorporate the classifier guidance. Yeah, so compare with the existing baseline model. So actually, we can see that the improvement is very significant. Yeah, and also it will also improve the robustness of the model in the future attack examples. Yeah, so besides the significant improvement in the first round, they also have very big improvement in the second and the third round of the adversarial examples. Yeah. So yeah, generally this is how is the takeaway from this method and this paper. So we can see that the synthetic data is still very useful if we want to improve the robustness of the model. And what we can learn from this paper is that we can just only have a very small set of the adversarial examples from human annotation, and we can utilize this as a seed to create the synthetic data set and scale. Yeah, and also another thing is that we can make use of good control decoding algorithm, like we can utilize the classifier to guide the generation so that we can generate good adversarial examples to further enhance the adversarial robustness. Yeah, so this is from my presentation. Yeah. Going to play the.
Is there a video for the other one? I
don't
didn't
know.
see it. Taha, do you know? Or Taha left already? Because I think he had to go. Yeah. Are there any other presenters that were not around?
This video is from. This is toxicity.
This is the toxicity video.
Good morning, everyone. I'll be
So it's
presenting
quite
on the topic of
sensitive. Go ahead.
toxicity in language model. The working definition of toxicity refers to anything that is rude, disrespectful, or unreasonable that will cause discomfort. In the paper Real Toxicity Prompts, Evaluating Neural Toxic Degeneration in Language Model, the finding shows that pre-trained neural language models such as the commonly used GPT are prone to generate toxic language. This includes prompts that do not contain any toxic words as shown in the figure. Hence, the motivation of the paper is to investigate if language models are safe to deploy for text generation and propose a framework to evaluate toxicity in a systematic way. There are 5 models being explored in the paper, GPT-1 to 3, and Conditional Transformer Language Model, CTRL, on Web Text and English Wikipedia. The models are being evaluated in a proposed framework, Real Toxicity Prompt, which contains a dataset of 100K sentence snippets. Toxicity of the generated text from the prompts are then measured by 2 metrics. The first being the expected maximum toxicity, which is the mean and standard deviation. A higher matrix implies more toxic generation. The second is empirical probability, which measures the probability of generating toxicity score of more than or equal to 0.5 at least once. A higher probability implies higher frequency of text generated being toxic. For this slide, I will walk through how the real toxicity prompts are being developed. Using the documents from Open Web Text corpus, the toxicity of the documents are being measured by Perspective API. Perspective API is a toxicity detector which evaluates documents with a toxicity score of 0 to 1. The 100K prompts are being selected via stratified sampling, with 25K sentences from each toxicity score range of, example, 0 to 0.5, followed by 0.25 to 0.5, and so on. The sentences from each of the prompts are then split into half using Spacy English Tokenizer into a prompt and continuation. This results in approximately 11.7K tokens in length. The prompts are then being rated for toxicity by the Perspective API to determine if it's a toxic or non-toxic prompt. For a prompt that has a toxicity score of more than or equal to 0.5, it is considered as a toxic prompt. The datasets are publicly available for download on the website set up by the authors. As a baseline, the 5 mentioned language models are being generated over n times with no prompts. The expected maximum toxicity is on the y-axis, and a score of more than or equals to 0.5 are considered to be toxic. The figure shows that it takes about 100 generations for all 5 models to degenerate into toxicity, and with over 1K generation, it is very likely to happen with a score of 0.9. GPT-3, the purple line, is trained on larger dataset, but the behavior mirrors GPT-2, the green line, which could be due to similar design in the training data. An interesting observation is that CTRL Wiki has significantly lower score than the rest of the LMs, which implies that models acquire toxicity in their pre-training data. The models are then being measured over 25 generations based on the real toxicity prompt to investigate the probability of toxic degeneration. It is expected for the toxic prompt to have a high probability, but what is surprising is that non-toxic prompt result in majority of the LLM generating toxicity close to half of the time. Even for CTRL Wiki, which is trained on Wikipedia, the probability is still high. Hence, it is important to look into methods to steer language models from toxic behavior, which the paper coined as detoxifying generations. GPT-2 is being used as the main model for detoxification. It is trained on 150K documents from OWTC. OWTC is a large corpus of English web text scraped from outbound URLs in submission on Reddit communities. The methods are grouped into two categories: database detoxification, consisting of domain adaptive pre-training, which is additional pre-training on non-toxic subset and toxic subsets separately. Attribute condition to implement additional pre-training with a toxicity attribute token. For the decoding-based detoxification, the first model is vocab shift to evaluate the vocabulary logics. Word filtering to implement a block list of a set of words and have the language model generation to a probability of 0 for these words. Plug and play language model PPLM alter past and present hidden representation using gradients from a discriminator to generate desired attributes. The result shows that DAPT trained on non-toxic subset and PPLN is the most effective with the lowest expected maximum toxicity score and lowest probability. Do note that PPLM is trained on 10K prompts instead of 100K prompts due to computational limitation. Hence, DAPT can be considered to perform better given that it's tested on a large larger dataset. Here's an example of the text generation result from prompting. All of the detoxified models are showing lower toxicity score as compared to the baseline GPT-2. However, there are a total of 3 to 7 prompts that cause all models to consistently generate toxicity, which perform better than the baseline of 1,225 prompts from the 5 out-of-the-box language models. Examples of these prompts are the 4 text prompts in the Pablo speech. Further investigation show that 2 to 5% of GPT-2 training data may be toxic. This data come from mainly low reliability news sites or from banned subreddits. The table shows the category of toxicity and its corresponding score on OWTC and OpenAI WT. From the result, it's evident that data selection process in language model is important and should be transparent. Adaptive pre-training shown to lower the tendency of LMs to generate toxic language, but may not be able to fully eliminate it at the moment. This may be due to toxic examples being more salient and it is hard for them to unlearn. In general, the paper serves as a test bed to evaluate degeneration in language models. I come to the end of the presentation. Thank you.
I know we have at least one project that's being done on tuning for safety and around toxicity. So we look forward to that project next week during steps. And I think we are way over time. So thanks for everyone for presenting today. So next week, we'll see you on Wednesday, okay? Wednesday afternoon. Again, that is the time of steps. And so I hope we will have a chance to share with each other how things are going there. Let me just finish up that, okay? So, okay, great. So that's all for today. Thanks so much. We have one more session on Friday next week, and then we're done.